Good morning, young learners. Today I'm very excited because I'm using a microphone. I think my voice will be clearer now from from the videos that I have been shooting for the last 3 months. Okay, I've tested it. I'm quite sure that it must be clearer. So let's begin. We are still in chapter number 2, the structure of atom, a chapter in class 11 chemistry NCERT textbook. We have taken out another question number 2.17. Calculate the wave number. The question is saying calculate the wave number for the longest wavelength transition in the Balmer series of atomic hydrogen. Yes, this is regarding we are required to calculate the wave number. I want to emphasize that what is wave number? Wave number is like how many waves are there in a unit length. That is the definition. How the number of waves present in one unit length. Unit length means what? Unit means one. That means in 1 meter how many waves are there, or in 1 centimeter, or in 1 millimeter, or in 1 kilometer. In unit length, what is the number of wave present in them? That is called wave number. So if the wavelength is very small, the wave number will be large, and if the wave number is and if the wavelength is long, then the wave number will be less. So there's a relationship between the wave number and the wavelength. In fact, wave number is reciprocal of wavelength. Wave number, it's the reciprocal of wavelength. Like frequency is a reciprocal of time period. Frequency is number of waves that are passing through a point in 1 second, and the time period is how many how much time it takes to cover one wave. That is called time period. So frequency and time period are reciprocal. Similarly, the wavelength and wave number are reciprocal. Yes, so you are required to calculate the wave number. The symbol is this, something like frequency is written, and over that we put a bar. This is the symbol of wave number, and it's regarding the transition in the Balmer series. So you understand what is Balmer series, yes, and it's happening in atomic hydrogen. So whether it's Balmer series or Parsons series or bracket P-Fun series, these are all related to. Please remember that these series are related to hydrogen atom, right? So this is like the spectra, when the radiation is allowed to pass through the hydrogen atom in its gaseous state. The spectra which is unique to the hydrogen atom is produced, and it can be seen in a film. And a textbook is shown to be passing through a prism. Then a film is a film, or just like a screen is made, and on the screen the spectra falls. It is line spectra. So there are various spectra that is formed depending upon. Later on we came to know that spectra is formed due to the jumping of electrons from a higher orbit to a lower orbit, right? Or absorption spectra is formed when electron jumps from a lower orbit to a higher orbit, which is from lower energy to the higher energy. Right. So in 1885, it's the Balmer series named after the scientist 1885 who discovered it. According to it, the wave number, the simple formula for wave number is 109677 multiplied by 1 by 2 square minus 1 by n square per centimeter. So in 1 centimeter, how many wave numbers? So this is a direct application of the relationship that we have given by the Balmer. We are not going by how this has come to although there is an explanation for how the wave number has come to this. That let's discuss that in another. Although I have discussed it in my earlier theory sections in another video, but in this particular for solving this particular question, we are not going to the how does this relationship has come. So we will just put in the value, but we will understand what to put. So this is 1 by 2 square minus 1 by n square, and what is what is the beauty about this equation is that we need to understand what will the only thing that you have to put is the n, right? And how do you know the value of n? According to the equation, the value of n should be more than 2. That means the electron has to jump in the 2, means it has to jump back to the second orbital. So it may be from from to the second orbit, from it maybe from third orbit to the second, or to the fourth to the second, or fifth to the second, or sixth to the second, but it has to jump the second orbit. So all those electromagnetic radiation and the corresponding line that is produced when it jumps, and those are called Balmer series. So Balmer series is not a single line. There will be many lines. Like for if an electron is jumping from second 6 to the second, there will be another line. 5 to the second, there will be another line. 4 to the second, there will be another line. So there will be many lines. But the question is talking about the longest wavelength. So longest wavelength corresponds to least energy, least frequency. Longest wavelength corresponds to least frequency, because you see for any electromagnetic wave, whether it is gamma rays or X-rays or ultraviolet rays or visible rays or microwave or radio wave, the product of the frequency and its corresponding wavelength and its corresponding frequency will be same. It's the speed of the electromagnetic wave, or it's the speed of the light in vacuum. That is 3 to 10 to the power 8 meters per second. So this is constant, but these two vary. So how do they vary? They are inversely proportional. If this is more, if wavelength is if frequency is less, wavelength will be long. If frequency is more, wavelength will be short, right? So these are inversely proportional. And again, how is frequency related to the photon, to the energy that is generated when it jumps from from higher level to the lower orbit, from higher orbit to the lower orbit? What happens is its energy comes in the form of photon, and energy in one photon is given by Max Planck's equation, E equal to h into nu, where h is the Planck's constant and nu is the frequency. So energy is dependent on a frequency, right? It's directly proportional. Here they are saying longest wavelength. So wavelength is again inversely is inversely proportional to frequency. The long wave means less frequency. Less frequency means less energy. So you have to think where will be the minimum energy when there is a jumping. So if you jump from a very high orbit, from a very high principal quantum number far away orbit to the second orbit, there will be large difference in energy. But if you jump from just the consecutive or the neighboring orbit, then it will be less. So the value of it has to jump to second. So the number which is the principal quantum number which is nearest to the second is third, right? So it will jump from third. Instead of jumping from 6 to second, or 5 to second, or 4 to second, it will jump from third to second. That will be minimum. Shortest jump means shortest amount of energy, mean least amount of energy, right? It will mean least amount of energy. So least amount of energy means least frequency. Least frequency means longest wavelength. So longest wavelength corresponds to shortest jump or smallest nearest quantum principal quantum number. So nearest principal quantum number to 2 is 3. So we put the value of 3 here. So this is the beauty of the question. Here you have to know what does the meaning of longest correspond to, longest wavelength correspond to. So we put the value of 3. Rest is the simplification, mathematical simplification. 1 by 4, 1 by minus 1 by 9. This will be 9 minus 4 divided by 36. 9 4 36 minus 4 5 by 36. So I have taken 36, 35, 5 7s are 35. I just taken rough value is average 7. I just took this 7. So 7 divided by this is 170,977 per centimeter. So in 1 centimeter there will be 17,000 wavelength, or in 1 meter there will be more. I added 2 zeros, so it's 1,70,000. No, 17,09,700 wavelength will be there. This particular wavelength will be there in 1 meter, right? I hope you have understood this.